So given that we have optimal adversarial strategies that are given by an MDP, how can we quantify security? So on the one side, we have optimal adversarial strategies. On the other side, we have honest behavior. So all we need to do is to quantify how much money can an adversary make by performing double spending or selfish mining, and how much can a miner make when performing honest mining. And we're going to compare those two. If the adversary behavior is superior in terms of monetary reward to the honest behavior, then like a rational adversary will choose to attack a chain. So that's why we quantify a so-called double spending threshold. So the profitability of a double spending depends on the transaction value, right? The higher the value, the higher the profitability of a double spend attack. And so if you look here at this particular plot, we can see here on the x-axis we have the stale block rate that's characterizing a blockchain, and on the y-axis we have a double spending threshold expressed in terms of block rewards. So if you look at this line, so this green component here, this is actually the safe zone. This is where a miner would perform honest mining, and everything above this threshold, right? This is the threshold here. An adversary would perform double spending. And here for this particular example, we assume that we have an adversary with 30% hash rate and 6 block confirmations that the vendor is waiting for the transaction to be accepted. And if you look at the stale block rate of Ethereum, so the stale block rate of Ethereum is about the stale block rate of Ethereum is about here, like about 7%, right? So you can see if you go up this plot here, you go here, you can see if the double spend value is more than 10 Ethereum block rewards, then there will be an adversary that probably does perform double spending, right? If the Ethereum value is I don't know, $100 or $400, then you know how much US dollar of value your transaction is, and you can basically quantify whether 6 block confirmations are sufficient, right? You always want to be in this green zone here where there's this honest mining regime, and you don't want to land in the double spending regime with your transaction. So if 6 block confirmations is not enough, you just increase this value, and then you should be safe to go. So given this methodology, we can now quantify the double spend confirmation time, right? So we have Ethereum, we have Bitcoin. So in Ethereum, we have 37 block confirmations. We find that 37 block confirmations are equivalent to 6 Bitcoin confirmations from a security point of view when considering a rational adversary with 30% of the total computing power. So if we translate this to time, that's about 10 minutes in Ethereum and about 60 minutes in Bitcoin. This means based on this model that we have and the MDP, Ethereum is about 6 times faster than the Bitcoin blockchain. We can do the same for other blockchains like Litecoin or Dogecoin, and that's why it's beautiful. It's like a generic framework where you can plug in any proof of work blockchain. So let's look at this last plot here. So, and let's spend a bit of time. It's not that simple. Maybe if you look at it first, but eventually it will make sense. So on the x-axis here, we have the adversarial mining power, the hash rate, right? So it goes from 0 to 50%, the hash rate. And on this axis, we have the double spending threshold. It's again the same double spending threshold as we had before, expressed in block rewards. And here we translate this to US dollar based on a particular US dollar value that we had at the time of performing this particular plot. Now, if we want to compare Bitcoin and Ethereum with 6 block confirmations, right? Let's do this here first. You can see these are these two lines, right? So there's a slight difference between Bitcoin and Ethereum. So actually Bitcoin is a bit safer from double spending, right? Because it's above, so the threshold is higher. Higher means it's safer. And this means we have because Ethereum's protocol is slightly different. There are anchor rewards that are also counting. So we model this in an MDP. So that's why you see a slight difference. Now, if we translate it to US dollar, right? So if you just look at the bare US dollar value, then you can see this is here the line for Ethereum, and this is the line for Bitcoin. So if you just look at it in terms of dollar, the Bitcoin, 6 Bitcoin block confirmations are certainly much more secure than 6 Ethereum block confirmations, which makes sense, right? Because the confirmation time in Bitcoin is much longer, and in Ethereum it's 10 minutes versus 15 or 12 to 15 seconds in Ethereum. Now, if we increase the block confirmation times to the number of block confirmations to 12, then you can see here that up to an adversary with 10% of the hash rate, Ethereum is actually safer, right? And then there's here this the crossing point between those two chains. But 12 block confirmations is much faster than 6 block confirmations in Bitcoin. So that's basically quite interesting, right? You can increase incrementally the number of block confirmations that you're willing to accept, and then you will see at 36 at an adversary with 30% of the hash rate, they will cross here those two lines, and this means you have you need about 36 block confirmations in Ethereum to match 6 Bitcoin block confirmations, right? And for an adversary with about 10% of the hash rate, you need 12 Ethereum block confirmations to match the security of 6 Bitcoin block confirmations, right? So this is the a measure to objectively compare different blockchains, depending on the adversary mining power that you're looking at. You always need to kind of adopt a model of what is an adversary that you're willing to accept, because you can't really generalize for every adversary, right? It always depends who is your opponent.